right, I thought we'd start playing commercials before each class. Oh, thank you. This is a very good commercial. All right, so welcome to the start of week 5. So, as you may recall, a couple weeks ago, someone cracked the iPhone, and then Apple updated the iPhone, thereby rendering those cracks unusable. Well, it took just a couple weeks, and someone did it again. So as promised, someone figured out how to do it. And I offer this really as an example of this reality in the world of computing and secure or insecure computing. The adversaries, the bad guys, for the most part, really do have the advantage out there. And this cat and mouse game is not unique to the iPhone. Constantly, there's been this struggle for years between good and evil, those who make software and those who try to crack software, simply because, among other things, it's the good guys that have the losing proposition. If the good guys want to ensure that their code, that their programs are secure, they effectively have to make sure that there are 0 bugs in that software, or at least 0 security-related bugs. Whereas the adversary, by contrast, only needs to do what in order to crack some piece of software or hardware? And he's only got to find one, and that's sort of an imbalanced playing field, and it's rather a reality. And it's also partly a reality because of the language in which a lot of software continues to be written, whether C or C++. And it's this week when we actually look at some of the coolest, some of the most powerful, but also some of the most dangerous functionality of C, namely pointers. But first, a couple of announcements. So there is a hacker section tonight, as well as this Wednesday night, the focus of which will be material tangential to the course, as well as the hacker edition of the problem set. So do check that out, 7 p.m. tonight in the MD Cafe. There's also a super section this Wednesday, which will focus not only on this past week's material, but also on GDB in particular. And this, again, is a tool that I would urge you to become comfortable with. Force yourself this coming week. When in doubt, don't put a printf statement in your code, but rather start playing around with GDB, even if it's just to print out variables. And over the term, I think you'll become even more savvy with experience. Finally, grades are beginning to go online. I finally finished the code that allows you all to integrate with our database and see by logging into the website what your scores are to confirm or deny that they're correct. So do keep an eye on that for the next 24, 48 hours once the TFs have uploaded everything there too. All right, so problem set 3. A word on this. So for those of you who have dived in already, you know that there are a couple of components to problem set 3, one of which is related to searching and sorting, the other of which is related to the game of 15. One thing that I'd like you to just see, if you haven't already, is the fact that no longer will you need to write GCC at the command line. As the PDF explains, we have tried to help you save keystrokes by using a tool henceforth called make, such that when you're in, for instance, the find subdirectory of problem set 3's code, compiling all of this code is as simple as typing the word make. And notice that that automatically triggered a couple of long GCC commands to get generated. But if now I type ls, you'll see there's a couple of programs that got built automatically. No longer do you need to specify the cryptic syntax at the prompt. This program, for instance, generate, is a program that's meant to generate n pseudo-random numbers. As the problem set explains, a pseudo-random number is essentially a random number, but not quite. Why is it the case that computers, for the most part, cannot truly generate random numbers? Yeah?
They're deterministic machines. They can't. Everything they do, you have to tell them what to do.
Yeah.
They can't do anything off their head.
Perfect. They can't do anything off the top of their head. They're deterministic devices, which means given some input, they produce the same output again and again. So we talk about pseudo-random numbers because through clever mathematical formulas can you create the appearance of uniform distributions of numbers over some range of values. But even then, it's not necessarily truly random in, say, the purely mathematical sense. Generate, then, is a program that generates those. You'll use that to generate numbers that you can then search and sort. And finally, you have in the 15 directory 15.c, which is similarly built by make. If you run it out of the box, what you will simply see is a program that, unfortunately, does very little. This is a game that hasn't yet been implemented, and we leave it to you to implement much of the innards of this so that you see exactly what we're talking about. Note that, as we've been doing for all of the problem sets thus far, we do provide not solution code, but solution binaries. YaoYu, for instance, implemented this version of 15. This is I'll call it super fancy version of 15. So realize that the bar isn't necessarily set this high, but she really did do a nice job. So notice when I run it, it asks me for D, the dimensions of the board. I'll go ahead and run it as the original game of 15. She used some neat ANSI escape sequences so that she could integrate a bit of color, which is optional for you all if you wish. And now the game is simply played as follows. Which tile do I want to move? Well, maybe I'll move 10, and it will figure out that 10 needs to move to the right-hand side. Maybe I'll move 9. It slides down. I'll move 6. Now I'll move 10, and so forth. And just if you're curious to see this go to fruition, the Hacker Edition this week not only has you implement this game, it also has you implement something called God Mode, which is a common term in a lot of games these days, a cheat really, where if you type something like God, well then the computer kind of helps you out. And in this case, Yao implemented an automated solution to the game. But that's not what you need to do. But it's quite cool that she pulled this off in color, no less. So if you watch that go, it will put all the numbers in order and color them green as they're fixed in place. So it's quite cool, and she got it working for even boards that are much larger. And I guess, do we want to get to the climax here? Let's see. Well, it'll get there. All right, that'll quickly take up too much. Oh, there we go. 7, 8. Oh, very nice. So we've won the game of 15. All right. So our thanks to Yao for that. All right, so the program itself, though. Take note, in 15.c, once you pull up your own version of the problem set, you'll see that we've given you a bunch of code, at least a main routine, which just zoomed by. But then, for the most part, this stuff down here, which is a bunch of additional functions, has blanks in it. To do, to do, to do. And essentially, because we're beginning now to develop larger programs, we didn't want to just throw you into the mix and have you figure out how to implement an entire game from scratch, especially one that's somewhat involved. So what we did with this problem set is provide you with a framework, really, holes that you need to fill in the form of a main routine that calls these various functions. So essentially, this game sits in the main function in what's essentially an infinite loop. So I'm going to scroll down. And again, we're breezing through some of this just to give you a sense of what to expect when you look at the PDF if you haven't already. But the game essentially sits in an infinite loop, waiting for the user to provide a move, provide a move. And every pass on this loop, the game checks, has the user won? So notice this line here that says if won is clearly in the form of a condition calling this function called 1. Unfortunately, 1 doesn't yet exist. We defined its declaration, but it just returns. It doesn't do anything. So it's going to be up to you to decide exactly how to figure out if the game has in fact been won. If it hasn't been won, though, as you saw with Yao's solution, it says tile to move. We then call getInt to figure out what number the user wants to move. And then we do this. So if exclamation point move tile. So what is that? So move is presumably a function. What's going on with tile there? Just use some C jargon here. What are we doing? What's that? Yeah, so we're calling the function move and passing in the variable tile as its argument. So presumably the function knows what to move. And then what's the deal with the exclamation point that's right in front of move? Yeah, so it negates the return value. So if you saw briefly, the return type for 1 is a bool, which means it returns true or false. Well, the idea of this condition here is simply that we expect that the move function will return true if the computer is able to make the move that the user specified by typing in the number, else it'll return false. If, for instance, the user chose a tile that's locked into the corner somewhere and physically can't be moved, that would result in false being returned. So what this is saying is that if it's not a valid move, go ahead and print illegal move, wait half a second, and then go ahead and, no matter what, wait another second just for the animation to pause for a moment. And then, as this suggests here, it goes back to the start of the loop and repeats again and again and again. So it's those holes that ultimately you'll need to fill in. We leave some of the design decisions to you, but hopefully you will feel, because of the way the spec walks you through this problem, that you can really approach it step by step by step. And here's the lesson. So we've seen in the lab over the past few weeks that many of you have this tendency to approach some of the problems on the problem sets sort of in whole. You take the problem like Visionaire and you sit down and you start writing 20, 30, 40, 50 lines of code. You cross your fingers, compile it, and inevitably, well, it certainly doesn't compile. And even when you get it compiling, well, what's then the case? odds are it doesn't even work, right? So the lesson there, hopefully, if you haven't caught on already, is quite literally take baby steps when implementing these programs. And I don't say that in a belittling sense. To this day, that at least is how I approach coding. Write small pieces of the program step by step, top to bottom, and get things working so that you're comfortable that at least you have something that's correct before you go on to make it more complicated. So consider Caesar for a verbal example. So Caesar, recall, was a program you needed to run at the command line, followed by a command line argument, which was what? So that was the key to use, the numeric key. So a simple program, for instance, the first step in implementing Caesar, especially if you're not quite sure where you're going to go with this, would be to write a very simple program called Caesar that simply expects a single command line argument and quits immediately if the user provided 0 arguments or maybe 2 or more arguments. Once that's working, go ahead and then check the validity of that argument. So version 2 of Caesar might have been check, is that thing actually an int? Right? So you probably had your for loop iterating over the digits that were in argv of 1. And if they're all numbers, great. Quit and say yes. Otherwise, quit and say no. Now you've got up to version 2 of your program. From there, take another step and actually now ask the user for a string. And then start iterating over that string and just rotate everything by k, whatever the keyword was, the key number that the user typed in. And don't even bother with the modulo stuff, because that too hung a few of you up for a bit of time. Don't worry about it. So what if z becomes some random character? At least most of the letters of the alphabet would have still worked at that point, version 3. And then finally in version 4 of Caesar, might you have then gone in and figured out, all right, how do you integrate modulo and actually finish this problem off? I mean, to be honest, that sort of mindset I think is invaluable when you're first starting these things, and even long term, to bite off these programs step by step so that not only do they compile, they're at least correct for at least a narrow definition of correctness. So with that said, the code that we're presenting with you tries to preach that lesson whereby we tell you which of these functions, for instance, which to implement first, then next, so that you at least build something from small on up to a larger program. So any questions on problem set 3 or anything else? Anything at all? All right, thanks. All right, so a look back at this thing. Oh, no, let's do this. Dead beef first. I almost forgot. So we've taught you, you know how to talk. You came into this course knowing decimal. We taught you on day 1 how to speak binary. Today, we're going to quickly teach you how to speak hexadecimal. Hexadecimal, aka base 16, means what? What are the implications? If I say we're going to write numbers in base 16 or hexadecimal? So I hear some murmurs. Yes, and back. We need what? So we need some new digits, right? So thus far, we've had at our disposal 0 through 9, but hexadecimal, or base 16, implies that we need now not 2, not 10, but 16 digits to represent numbers with. So hexadecimal simply uses not only 0 through 9, but also, for those familiar? Yeah, so A through F. So in other words, using just a single hex digit, what's the largest decimal value that you can count up to? Yeah, so 15, right? So 0 through 9, then A is 10, then B is 11, then C is 12, dot, 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 F is 15. So what are the implications? Well, again, the process is identical in spirit to how you represented binary numbers, but these things are useful in a lot of programmatic contexts, which is why we mention them today. So if you ever see in a program 0x before some number, that simply tells the compiler this is a number in hexadecimal. Okay, so the x doesn't have any special significance other than that. If then I write, for instance, my program, int x gets that, well, what integer is stored in x at the moment, do you think? All right, so pretty simple. It's just 0. What if we expand on this a bit and we say, all right, so 0xa is going to get stored in my variable x. Now we have the value we know as 10 in there. All right, let's make it a little more interesting. Suppose instead we don't do a, but now let's actually represent, say, FF. So 2 digits next to each other. What's that? OK, so fewer immediate responses. And before I shout out the right answer, at least, let's think about what each of these means. So how many bits do you need to represent any of 16 possible digits? All right, so just 4. You can get away with 4, because if you have 4 bits, that means you can represent 2 to the 4 possible different values. So the implication, that's 16. So if you only have 16 digits, effectively what hex is in binary is as follows. Let's say that, let's make some room here. So 0 in hex equals 0, 0, 0, 0, according to this logic of using only 4 bits. 1, meanwhile, equals 0, 0, 0, 1. Dot, dot, dot. E equals, with a value 14. Well, how do we represent that in binary? Right? So a 2's, a 4, an 8, 14. Yeah? OK, so finally F, then, easier. 1, 1, 1, 1. OK, so now, at least with that translation in mind, what do we mean when we say int x gets 0x ff? Well, that's effectively saying int x gets the binary number that's 1, 1, 1, 1, 1, 1, 1, 1, which is what? Yeah, so 255, right? When we talked about 8-bit values, if you set them all equal to 1 back in our binary discussion, that's just the value 255. So we won't dwell on hexadecimal numbers because there's not all that much sexy about them here, but know that it's often a more efficient way of representing large numbers compactly in a program. For instance, how many of you recall off the top of your head what 2 to the 32 minus 1 is? You have roughly 4 billion, but that won't cut it in a computer program. So it's 4 comma, yeah, I don't recall either. But how can we actually represent this thing without calling, for instance, the POW function, or without actually computing it somehow in memory? Well, if we want to represent the number 4 billion, well, essentially, that's what? Well, 1, 1, 1, 1, 1, 1, 1, 1. So that's 8 bits, right? And actually, whoops, I'm writing in binary. That's 8 bits. That's another 8 bits. That's another 8 bits. That's another 8 bits. So there's 2 to the 32 presented, minus 1, presented in hexadecimal. And there's a little gotcha there. If you want to put this number in a program, it actually won't fit in an int. Why? The value 4 billion. Sorry? Right, because if we try putting this in an int, like int x, we're going to get effectively overflow. If we mean to put 4 billion something in there, this won't fit. But if we make this instead unsigned x, we will, in fact, fit the value 2 to the 32 minus 1. OK, so tuck that away. We'll see this not only in C, but also several weeks from now when we start doing website stuff and you look at HTML perhaps for the first time, we'll see hexadecimal is actually used as color codes. If you ever wondered why things in HTML are like color equals quote unquote FF, well, that represents white. Well, that just means it's as much. OK, we'll get there. But that means red, green, blue. A lot of red, a lot of green, a lot of blue, which according to the spectrum of light means a lot of whiteness. OK, but that's a sneak preview. Dead beef. Why was this the intro here? So it happens to be a stupid phrase you can spell in hexadecimal. And you'll see this occasionally in code written by true geeks where they want to have like some special sentinel value, some value that isn't expected to be in the code unless they put it there intentionally. And this just tends to be a trick that some folks have used over the years. So in any case, back to this stuff at hand. So here's a look back at buggy3.c from a couple weeks ago now. Why was this thing called buggy? Yeah, and back. Good. So it didn't actually do what it promised to do. It did not swap values. So recall that, and I put this in this week's directory as well. We'll bring printouts of everything likely on Wednesday for all the code we use this week. If I go ahead into this directory. Oh, and notice, too, that in addition to problem set 3 giving you these things called make-files, if you've read over the spec, recall from last Friday that if you just have a C file like buggy3, no longer, too, do you need to type gcc, buggy3.c, and so forth. You can just type buggy3, and make will figure out, it doesn't need a make-file, it will figure out how to build that thing for you. I'm going to go ahead and run buggy3. Notice that this is what we saw a couple weeks ago. Clearly, it claimed to be swapping, and it didn't. But why was that? Why was this broken? It's the same code as a couple weeks ago. Yeah, so this was the issue of variable scope. So we said back then that in this program, buggy 3, we did indeed have main declaring a variable x and a variable called y. And then we printed them out as you just saw. Then we said swapping ... and then we passed them. But we passed them by value, which means quite literally that what become of x and y with respect to a and b? Or what's the relationship between x and y and a and b precisely? So they're copies, quite literally. So yes, a is the same value as x, and b is the same value of y, but it's its own chunk of memory in the computer's memory space. In fact, where, in terms of that picture we've seen a few times now of a program's memory space, are a and b living at the point that swap is being called? Yeah, so it's on the top of the so-called stack, which simply means for our purposes that they have their own chunk of RAM reserved to them. They each have their own 32 bits assigned to them. So did these 3 lines of code indeed swap A and B successfully? OK, so they did, right? That is a perfect swap. We're using a temporary variable, so we don't clobber one value, but it did work. But the moment that function returned, what was still true, obviously, about x and y? Well, we hadn't even touched x and y literally because we had only passed in copies of those variables. And we promised a couple of weeks ago that there is indeed a solution to this problem. And today, and this week, we focus on it and the implications of the solution. Here's the after. And just to go back, before, after, before, after. So what is clearly different? So it sounds like the problem is the fact that the variables are being copied, when we really, in the sense of swapping, want to pass in the variables themselves. But by default, if you just pass a variable and call it A and call it B, by C conventions, you get a copy. But if you literally want to pass the original variable to the function, you can pass it, so to speak, by reference. And the means by which you specify that you're passing something by reference is that in the declaration of the function, you specify that a typo. OK. Let's fix this lest we start this off completely on the wrong foot. Whew. Yeah, good exercise. But I caught it first, which means it never happened. So here we have declared in the function's declaration that swap does take 2 arguments called a and b. But these things henceforth are not just ints, because they now have this star character there. They are rather pointers to integers. And as that word kind of conjures up, it's literally like passing in a pointer, like a finger pointing to where in memory the variables x and y in our example program literally are. However, if you're passing in the location, that is the address of x and y, by way of this syntax, you can't just then start saying a gets b and b gets temp and so forth. Because in this case, in this pass by reference, what's literally stored in a and b is the address in memory of those variables x and y. So if you want to change the contents of those variables, you need to change your syntax somewhat. So first, let's confirm that this does, in fact, work. So in swap1.c, we do, in fact, have the function declared correctly in the code here. And this is just a main routine. It's identical to buggy 3, except that I'm calling this version of swap. And I'll point out some other syntax in a moment. So if I run make swap1, go ahead and run swap1, notice that it did, in fact, work this time. So let's tease apart exactly why this is. So think back to that example of your stack. So in your stack here, we'll draw it bottom up like a tray of cafeteria trays, a stack of cafeteria trays. Here's main's frame on the stack. And the convention, again, was when you call a function, it gets put on top, on top, on top. So when swap is actually called, the memory it's going to use is going to be here. OK, but main has at least 2 variables inside of it. And so those variables are called x, and another variable, which we'll just assume is right next to it because they were declared one after the other, but that's not necessarily the case, is called y. OK, and what was the first thing we did then in main with those variables? I'll pull up swap1 again. All right, so we initialized x to 1, which means literally stored there is the value 1, and we stored 2 and y, which means literally 2 is stored there. Now, what we've been not drawing thus far in this picture is that this does represent memory, right? So this is just your RAM presented in a picture. But RAM is just a whole bunch of bytes or megabytes. Well, and if there are a whole bunch of megabytes, well, clearly you can talk about those bytes individually. The 0th byte, the 1st byte, the 2nd byte, the 3rd byte, and so forth. So we'll keep things slightly cryptic because it doesn't matter exactly what the addresses are. But let's just suppose, for the sake of argument, that this is the first byte in memory in your computer's RAM. And again, this is a bit of a simplification, but right there, this chunk of memory is the first byte. Meanwhile, the byte that starts here is 0x4. Now, wait a minute. Why did I say 4 instead of 1? Right. So not bits, but right. So each int is 4 bytes. So that is to say that this thing should be offset by 4. OK? But otherwise, the takeaway is the same. So if this is your computer's RAM, that chip inside your computer, and x happens to go at the very bottom left of it conceptually at the 0th address, and y is going to go as close to it as possible, so 4 bytes later, 32 bits later, this is what the contents of memory look like. In our original version of buggy 3.c, when we passed by value, well, what was happening? Well, in swap's frame, it too was getting a chunk of memory called A and a chunk of memory called B. It was then putting in there 1 and 2 the moment the function was called. And what else did swap put on its so-called frame? Yeah, so it also had temp. So again, local variables, as the word implies, also goes in this frame. That thing was called temp. And we put in it what? The value that's in A. So, right, so temp gets A just means temp gets A. So that's step 1. Then we said A gets B. So A gets B. So that meant that in buggy 3, that just happened. And then the third and final step, B gets temp. So B gets 1. OK? What happens at this point? Well, 2 and 1 are indeed swapped, but the function now returns. And I won't ruin our work completely. But what literally happens? All of this goes away the moment the function is done. Right? And then main stuff is still on the stack. But unfortunately, x and y were clearly unchanged. OK, temp2 just goes away. So what's going on now in the correct approach to this problem? Well, in this case now, notice what's happening. So now we have, again, arguments called A and B. All right, but A and B are declared as pointers to ints. OK, so pointers are just 32-bit chunks of memory that by definition are the address of something else in memory, the numeric location in memory. So when I pass now x and y to the correct version of swap, it's not 1 and 2 that get copied into A and B, but what, according to this idea? The address. So OXO and OX4. So slightly different. So now we're copying the address in memory of those variables. Meanwhile, what is temp? What data type is temp, apparently? So it's still an int. So it's still an int as up there. So it looks the same. And by coincidence, it's also 32 bits. The reason, as an aside, is that a pointer is just an int by definition in C. All right, so what happens next? So temp gets star A. So this is a bit of different syntax. We don't want to just say temp gets A. Otherwise, we'd be putting the address of A in temp. And that's probably not really what we want to do. What we want to do is hold on to that original value. So if I instead say temp gets star of A, the star operator is the so-called dereference operator. The star operator, when you put it right in front of a variable that is itself a pointer, which A absolutely is, given what we've said, the star has the effect of telling the computer to go follow that address and grab whatever's at that address physically. So in that sense, when we say star A, the computer realizes, OK, that's an address. It's 0x0. The star means to go follow that location. And so it jumps to that location in memory and realizes, OK, I see the value 1 at that address. And so temp gets the value 1. OK, step 2, star A, star B. Someone else explain this story. It's twice as many pointers, but story's the same. What's going on? Anyone?
The thing that A points at is given the value that B points at.
Perfect. So the thing that A points at is given the value that B points at. So what does that mean? Well, star A literally means go to now the location that A is pointing to. So what's in A? 0x0 is in A. Star means go to that address. All right, so here we are. What's it now telling me to do? Put the value of star B. Well, what's star B? Well, B is 0x4. The star means go look up that address, which is here, and look at what's in there. So what happens now? What do I need to erase and redraw on the board? Sorry? So delete this 1 and write in 2. Because star A means grab the address from A, dereference it, that is, follow it to the actual location in memory, and put whatever's in question there. And the same goes for B. Final step. So now temp, again, is just an int. So that's a nice thing. We don't have to even worry about any pointers or dereferencing there. But B, so star B. So B is a location, a pointer, an address. These are synonyms at this point. Star means go to that address. Well, that's the address. What do I want to put there? I want to put temp. And so now we go and put the value 1. So that's it. So when people talk about pointers in the context of a program, all they're talking about is the address of something in memory. And this is perhaps the lowest level explanation of how you can define a pointer, but that's really all there is to it. And we'll see some neat features of pointers and what you can actually do with them that's useful, but that essentially is the story. Now, those of you who are particularly nitpicky, the lies that I've just told is that you can't store stuff at 0x0 by definition, right? If any of you have ever gotten a seg fault, it could have been because you tried to touch this memory location, and we'll see instances of this mistake. This is so-called null, if you've seen that in some of our examples thus far. So this, again, is a simplification. The addresses are going to be a little more cryptic, but let's actually take a look just to be convinced that this is real. So in bar.c, we have a, actually, no, let's do the same function. So in swap1.c, we again have this code. So we have the main routine, and then we have the swap function. What I'm going to do is go ahead and run GDB on swap1. So recall that I can type break main to set a breakpoint in main. I can then run this program, as we saw Friday, and this literally just stopped me at the first line in main. If I go ahead now and print out print x, what should I see? OK, so I do see 1, though I actually got lucky there. So let's see what's next. So I'm going to hit next. So print y. What should I see? 2. But what if I hit print amper, and p is a synonym for print to save you keystrokes, p ampersand x. This is the one last bit of syntax that we didn't draw our attention to. And I had it in a typo context, but we used it elsewhere. So if I put ampersand x, take a guess as to what that means, given what the story's been about. Yeah, that's just the so-called addressive operator. If you want to get not the value in some variable, but the physical location of that variable in your computer's memory, you just say ampersand x. So here's where it is cryptic. It is hexadecimal, but notice that's clearly not 0x0. That's actually a pretty big value, but that's because the computer's put a lot of stuff in memory at this point. So it's not quite at the start of your RAM. It's somewhere in the middle, essentially, though even that's a simplification because of virtual memory. But notice how this is relevant. In swap1.c, again, here's my main routine, but notice that it wasn't sufficient just to change the declaration of swap itself down here. I also had to make one other change. I had to pass to swap, not x and y, but to be clear, what? Yeah, the addresses of x and y. So this is why it's called a pointer. You're passing a pointer to the function, like a hint as to where it should go to find the values that you actually care about. So even though technically it's not to make this too complicated, but it's passing the value of, let me not say that. OK. I was going to make a subtle distinction that is only likely, I think, to confuse. So I retract. All right. What about this, though? Here's a slightly new and improved version here, because it's possible that my previous code could screw up, and it could seg fault. So some of you have seen seg faults before. Name one instance, even in lecture perhaps, where we've seen a seg fault. And why did we see it? What happened? What did I do wrong? Come now, some of you have had seg faults. If any of you have submitted to us a core file, we know who's had seg faults.
Is that where you iterated through string beyond?
Sure. Yeah, we've definitely seen it there. When I got really bold one day, and I think I looped not over just the length of my array or my string, but I went way the hell to the bounds of memory. And by the time I hit the 1,000th location or something, the computer bailed on me and said seg fault because I was touching memory that didn't belong to me. So similarly does this happen if your pointers are invalid. So by default, the convention is typically to initialize a pointer to null. Null is just the synonym, it's all caps, for 0x0, which is why I mentioned earlier this was a bit of a white lie. So that programmers can try to detect mistakes when it comes to writing pointers. 0, that is 0x0, aka null, is sort of a special value, a nickname that means that the pointer is invalid. So technically, with this previous version, swap 1, excuse me, I'm taking a leap of faith here. And I'm taking a leap of faith that what is in fact true about A and B? Sorry? So that they're not starting off as null or some bogus value. I'm trusting with this function that A and B are not only pointers, but they're valid pointers. That is, they actually point to 2 integers in memory and not some bogus or random address. Okay? This version, though, just adds a condition. So we have a Boolean expression with a couple conditions here. So if A is not equal to null and B is not equal to null, this is slightly more safe, because at least I'm not going to create a seg fault by foolishly dereferencing null, aka 0. Okay, so why is this perhaps... This is useful in that we can detect null, but what about this? Let's break our own code here. In swap 1, notice that up here I've declared x and y to equal 1 and 2 respectively. But you can declare pointers just like you can variables. That's declaring a variable. That's declaring a pointer to a variable, specifically a pointer to an int. What this has just done is when main runs now, x and y are indeed 32-bit chunks of memory, but this time they're declared as pointers, not as ints. So what if I now run this program? I only need to pass to swap 2 pointers. So I don't need to do the address of a pointer. That would get us into sort of a weird state. So when it's already a pointer, you just pass it. When it's a variable whose address you want, then you use ampersand. So in this case, x and y are already pointers. I'm passing swap of x and y here. So what now is going to happen when I run this code? Was this pencil thrown or accidentally tossed across the room? How's that for undue attention? So what's going to happen if I run this program? Well, mechanically, what's going on here? If this is what my state of my world looks like, what are x and y initialized to now? You know, ideally, but again, we've tried to emphasize that you should never trust what your variables are initialized to. All right? And sometimes you can get lucky and they'll be initialized to, say, zeros. But often, especially if there are local variables within functions, that's not going to be the case. So the safest rule of thumb is to just assume that if you don't actually put some value in a variable yourself, who knows what it is? It could be some garbage value, it could be 0, it could be any number at all. So if that's the case, and now I call swap, what might happen? Well, suppose that just for whatever reason, what happens to be in here isn't a question mark, but is some crazy large address like 0xFFFF, which is pretty big, certainly compared to the numbers we've talked about. Where is that address? Well, according to this picture, it's like up here. So what is swap going to try to do? It's going to try to put the contents of this memory, and maybe if this guy is similarly a big address somewhere up there, swap is going to work. It's going to swap the value that's here and put it here, and it's going to swap the value that's here and put it there, but who the heck knows what's there? In fact, recall that picture of our memory space. What is higher up in this diagram, if you recall? So it was a whole rectangle, and it kept going up. But there was this thing called the text segment eventually. The text segment is just the zeros and ones that represent your functions. That is your actual code. So these iPhone things that we've talked about and a lot of exploits of code these days ultimately boil down to people cracking software because by using pointers incorrectly or really maliciously, they're able to change what's going on inside your program by just overwriting values at will. And that's often the result of manipulating pointers like this. If you write a poorly defined function that doesn't check the validity of them, or worse yet, we'll see on Wednesday some functions that make this problem even worse, where you can actually, as an adversary, insert your own program into someone's program and have yours run instead of theirs, which means you can effectively take over their machine. So it's some scary stuff. So we'll see a couple of more examples now of how these things are working. So there's a good tutorial that you should check out at some point this week if you want on the website of How Stuff Works, which gives these pictures among others. But this, I think I will just wave my hands at, since these are essentially the pictures that we've drawn here. Let's tease this one up. Actually, let's go ahead and tease this apart. So this picture here is essentially telling us that if you write code like that, int I, comma j, what you're literally getting in memory is a box of RAM called I, and another box of RAM called j. And how big are each of those boxes? Quick. So 4 bytes, aka 32 bits, okay, because they're just ints. But if you then say int star p, you're also getting another chunk of memory, which the How Stuff Works people have simply by convention drawn as a circle, just to distinguish it. In this case called p. How big is it? 32 bits, aka 4 bytes, because all pointers, no matter what they point to, are in fact 32 bits. And what this picture is suggesting is that if you just declare, as they've done, int star p without assigning it a variable, they drew three arrows where I just drew a question mark, but the point is the same. Who knows what it points to? But if you add a line of code beneath those two that says this, star p gets the address of I. So what is this doing with respect to p? So p is a pointer by definition, which means it's the address of something. OK? So what is I? I is an int. What's ampersand I? Yeah, so that's the location of. They shouldn't have done that. There. OK, we'll fix that too. I'll take a look at their picture and make sure it's not my fault again. So here, p is a pointer. So what's ampersand I? The address of I. And so it makes sense to store that in p. OK, and I'll fix this too. Sorry about that. OK, so pictorially now, here's where you can really think of pointers as pointing. When you store the address of I in p, that's like storing the address like 0x whatever. But it quickly becomes tedious to think about pointers in that sense. Literally, if ampersand I is the address of I, and you're storing that address in p, it's as though this pointer p is pointing, quote unquote, to that variable. And so the notation that you'll typically see in a book, in class, and I think the better way of thinking about it mentally, once you're comfortable with the reality of what's going on underneath the hood, is that p is just pointing, literally with an arrow, to the variable's address that it was assigned. Finally, and this syntax is correct, if I say star p gets 5, someone propose what this last line of code does. So p is a pointer. So what does star p imply again? So go to the address that's in p, and then do what at that address? Right, 5. So pictorially what this means is go to the address that's in p, that is follow the so-called arrow, and put at its destination the value 5. So same stuff that we just described at a lower level, but it's sort of easier perhaps to think of it pictorially in this way, as pointers pointing to some address in memory. OK, questions on what you've just seen? Yes? No? All right. Why do you need? Oh, good question. So why do you need the star at the bottom here? What would it mean if I instead just said p gets 5? Right, so it would mean that we're storing literally the value 5 in p, and that might be OK, but what it connotes is that 5 is some address in memory. So if I subsequently said star p, and that is follow what's in p, and I had assigned it not to I like that, but instead I said p gets 5, what that literally means is point p to memory location 0x5, and who knows what's there. That's the problem. Good. Other questions? So I declared p, and they declared p at the very top of the program that we're taking piece by piece out of context here.
But why does it need to be declared as a pointer? Because so far we're just using it as an int, like it stores something on there.
So you can think of pointers as essentially a continuation of this idea of a data type. So if you don't want to get yelled at by the compiler that you're abusing a data type, you need to tell it explicitly how you're going to proceed to treat that variable. So if you want a variable to be treated in your own code as a pointer, you need to proactively tell the compiler that it is to be a pointer and not just an integer. Otherwise, you'll essentially get compiler warnings, even though you can ignore them and you can throw away a variable's type in C by casting, as we've seen. It's just bad practice to do that. But another good question. Others? Yeah, in back.
If stores a pointer as a 32-bit integer,
Uh-huh.
what happens in systems that have multiple gigabytes of memory?
Ah, an excellent question. Let me defer to that until we get a little deeper this week, but it's a great question. And just to rephrase, if pointers are just 32 bits, the implication is your arrow can only reach sort of so far up in memory. And the implication is that it seems to be that there's a bound on the amount of memory that your process can use. And actually, that's the short answer, that systems, yes, can use multiple chunks of memory, but often processes themselves are limited to less than that, even though you can run multiple processes at once. All right, so let's, you know what? Let's call it a day, and we'll continue on Wednesday.